Greetings to all, and welcome back to the course on homogeneous catalysis. The present module is devoted to CH activation. In this lecture, I will provide a general overview of CH activation. In the following lectures, I will describe the factors controlling reactivity and selectivity in CH transformations, as well as the main mechanisms in CH activation. This will be followed by lectures devoted to the modern directions in CH activation. Finally, I will present selected works on the practical applications of CH transformations. Let's start with definitions. First of all, it should be mentioned that in the modern chemical literature, quite often you may face other synonyms of CH activation. The most commonly applied synonyms are CH transformation and CH functionalization. However, depending on the specific transformation, you may see a number of other synonyms, such as CH arylation, CH amination, CH halogenation, etc. The most frequently used definition for CH activation was given by Bergman, which is as follows. Most generally, CH activation means treating a CH bond in some way that allows a reagent to react rapidly with the carbon atom. This activation can be achieved by most transition metals, which can serve as catalysts. As you may recall from the preceding module on cross-couplings, in organic chemistry, a cross-coupling reaction is a reaction where two fragments are joined together with the aid of a metal catalyst. Here, it is not important what type of bonds are being activated in the process of joining two fragments together. In other words, CH activations can be considered a specific case of cross-couplings, where at least one CH bond is activated in the process of constructing a new bond. As you will learn later in this module, CH activations have many similarities with the cross-couplings studied earlier. Besides cross-couplings, there is another group of well-known transformations that can be confused with CH activations. I'm talking about electrophilic aromatic substitutions. Here too, CH bonds are transformed into carbon-carbon or carbon-heteroatom bonds, and very often, this process is facilitated by an acid used as a catalyst. Electrophilic aromatic substitutions are not considered CH activations because the catalyst does not activate the CH bonds. Instead, it is responsible for the generation of cationic intermediates. Moreover, electrophilic aromatic substitutions have many drawbacks and limitations. They are confined to aromatic compounds and are effective only on electron-rich systems. Another significant issue is the poor selectivity and the necessity to employ highly reactive and corrosive reagents. For instance, let's consider nitration. It works effectively only for electron-rich systems like phenols, and stopping the reaction after introducing one nitro group is challenging. Attempting to do so will likely result in a mixture of regioisomers, and in addition, it may lead to a significant explosion. Modern developments in transition metal-catalyzed CH transformations address most of the problems inherent to electrophilic aromatic substitution. As I will demonstrate later, using transition metal catalysis allows for the selective functionalization of all classes of organic compounds, including electron-deficient aroms and aliphatic compounds. To the best of my knowledge, the first transition metal-catalyzed CH transformation was developed by Fujiwara and his co-workers in 1967. Initially, they found that stoichiometric quantities of palladium acetate could be used for the olefination of benzene with styrene. Furthermore, they discovered that, in the presence of an oxidant, palladium acetate could be used as a catalyst. In the beginning of the 1970s, Schulpen and Shilov developed the platinum-catalyzed CH halogenation and hydroxylation of alkanes. In the case of halogenation, they demonstrated that the reaction does not involve radicals, which is in agreement with the halogenation of the terminal methyl group. This is not typical for radical halogenation, which predominantly occurs at secondary carbons. Further progress was achieved again in Fujiwara's group in the 1980s. They showed that unfunctionalized benzene can be carboxylated using palladium catalysis and carbon monoxide. The rhodium-catalyzed CH insertion of carbons was developed during the same period. This topic will be covered in detail in the lecture devoted to metal-carbene complexes. The final, historically important CH transformation I want to highlight is the iridium-catalyzed olefination of alkanes developed by Felkin and Crabtree during the 80s. This reaction later found some industrial applications. Now, let's see how popular this topic is and why it became so popular. On this chart, one can observe the number of publications per year in the field of CH activation. The number of articles has been growing exponentially, especially within the last decade, crossing the threshold of 1,000 articles per year for 2016 and 2017. Some CH transformations are quite popular, while others are not. For instance, in 2017, the number of papers on CH arylation was almost 250. On CH amination, we had about 200 papers, while works on CH carboxylation were around 10. On the last chart, one can see the comparison of CH transformations in sp2 and sp3 hybridized systems. The sp2-CH activations are much more popular, which can be explained by the increased reactivity of aromatic systems and the ease of dealing with purification and separation of products derived from aromatics. To understand why this field is so popular, let's go through two examples. First, let's consider the synthesis of biaryls. Traditional approaches to biaryls are based on well-known cross-coupling reactions between aryl organometallics and aryl halides or pseudohalides, such as Suzuki coupling. In this case, one needs to first prepare the starting aryl halide and organometallic reagent from commercially available chemicals. The preparation of aryl organometallics is particularly difficult and time-consuming. Besides, it might involve the use of highly reactive and dangerous chemicals, such as butyllithium. On the other hand, modern developments in CH activation allow the direct assembly of unfunctionalized aryns. As a second example, let's consider the preparation of secondary amines. The traditional approach involves the use of alkyl halides, which must be isolated from other isomers formed during radical halogenation. This is not an easy task, however, the real challenge lies ahead. Stopping the reaction at the secondary amine stage is extremely difficult. The typical outcome of SN2 alkylation at nitrogen is the formation of a mixture of amines and a quaternary ammonium salt. Modern developments in CH activation offer solutions to overcome these challenges. Based on the numbers from previous charts and these examples, you might have the impression that direct CH activations are the easiest transformations one could possibly try to employ to address the issues you are facing in your projects involving cross-couplings. Unfortunately, CH transformations are not as straightforward as they might seem, and this promising field of research is still in its infancy. To sum it up, in this lecture, you have been introduced to the main definitions of CH activation. We compared CH transformations with other relevant reactions, and I provided a brief historical overview of the development of this field of research. In the following lecture, I will describe the main drawbacks that limit the widespread application of CH activations, along with some potential solutions for these limitations. Thank you for your attention. Hello everyone, and welcome back to the series of lectures on CH activation. In the previous learning material, you were introduced to the most important definitions regarding CH activation. In this lecture, I will describe the main strategies enabling selective CH transformations and discuss issues related to the reactivity of different CH bonds. There are two major challenges limiting this chemistry, as in many other cases, issues related to reactivity and selectivity. For instance, in benzene, all CH bonds are equal. However, by changing one of the carbons to nitrogen, we get pyridine, which has three different types of CH bonds. Adding a benzene ring to pyridine gives us quinoline, in which all CH bonds are different. Similarly, in piperidine, we have three different types of CH bonds, and so on. The question is, how can we differentiate these CH bonds from each other when conducting a CH transformation? Another question is, what factors determine and control the reactivity of these systems? You will soon learn that under proper conditions, these systems can be quite active for CH transformations, and acceptable selectivities are achievable. When speaking about reactivity, it should be noted that among aromatic compounds, the most reactive systems are electron-rich aryns, such as phenols and their derivatives, 5-membered heterocycles, and fused 5-membered heterocycles. The reactivity trends in CH activation are very similar to those observed in electrophilic aromatic substitutions. You will understand the reasons controlling the reactivity in sp2 hybridized CH bonds when we come to the mechanisms of CH activation. Among aliphatic systems, the most reactive compounds are the so-called CH acids, saturated heterocycles, ethers, and related aliphatic compounds possessing a heteroatom. In contrast, electron-deficient aryns and unfunctionalized alkanes or paraffins are quite inert. The reactivity of these systems can be significantly enhanced by the introduction of special functional groups, which I will show you soon. Due to their pronounced inertness, these systems are frequently used as solvents in homogeneous catalysis. In the context of CH transformations, it is important to highlight that, in certain categories of aromatic and aliphatic compounds, specific CH bonds show markedly greater reactivity than their counterparts. For instance, in 5-membered heterocycles like thiophene and pyrroles, the CH bond at position 2 is usually more reactive in transition metal-catalyzed CH transformations. Enhanced reactivity at position 2 is in good agreement with the analogous reactivity pattern for electrophilic aromatic substitution. Similarly, in indoles, the most reactive CH bond is the one located at position 3. In oxazoles, imidazoles, and related fused heterocycles, the most reactive CH bond is the one located between 2 heteroatoms, as the CH bond at this position is more acidic. Among saturated heterocycles, the most reactive CH bonds are located at the alpha position to the heteroatom. Here as well, the presence of a heteroatom makes the alpha CH bonds more acidic. It should be noted that depending on the reaction conditions and especially on the used transition metal, the reactivity may alter. Most of the studies in this field were performed using palladium-based catalysts. In addition to empirical studies, there are numerous theoretical studies devoted to palladium-catalyzed CH transformations. For many aromatic systems, the Gibbs-free energies of palladium-catalyzed CH activation were calculated and are presented here, with the most reactive CH bonds indicated in red. Once more, I want to emphasize that systems possessing a CH bond with increased reactivity are extremely limited. The first transition metal-catalyzed CH transformations were developed in the 1960s. However, until the 21st century, this field of research was not really popular. The main reasons were poor reactivity of CH bonds, limited scope, and a lack of selectivity. A real breakthrough in this field was the introduction of so-called directing groups. Directing groups are functional groups possessing a heteroatom with lone pairs of electrons that can coordinate to the catalyst. Acting as ligands, directing groups guide the catalyst to the position that needs to be functionalized. In doing so, they are able to address the issues of selectivity and reactivity. Here, you can see the range of directing groups developed within the last 2 decades. Among others, the most popular directing groups are those based on pyridines, amides, and Schiff bases. As mentioned earlier, unfunctionalized alkanes are generally unreactive. However, the introduction of a directing group into paraffins can dramatically alter known reactivity patterns. Consider this example published in 2011, the palladium-catalyzed arylation of cyclohexane, which possesses a pyridine-based directing group, leads to arylated cyclohexane in good yield and excellent regioselectivity. Under these conditions, unfunctionalized cyclohexane is not reactive. In this work, the authors demonstrated the role of the directing group by isolating a palladicycle where the catalyst is coordinated by the directing group. Let me show you another example based on the rhodium-catalyzed alkylation of indoles. Rhodium-catalyzed alkylation of unfunctionalized indoles occurs at position 3. However, the introduction of a directing group alters the selectivity to position 2. These examples show that if you have a proper directing group in the molecule, the directing effects are more dominant than the inherent reactivity of the given system. The introduction of the main directing groups was crucial for the development of this field and has allowed scientists to achieve many challenging CH activations. Here, I present the main carbon-carbon bond-forming CH transformations. Using modern developments in this field, we can introduce aryl, alkenyl, alkenyl, trifluoromethyl, alkyl, cyano, carbonyl, and carboxyl groups via CH activation. The main carbon heteroatom bond-forming reactions are shown here. Using CH activation, it is possible to introduce halogens, organometallic functionalities, amino groups, chalcogens, hydroxy, azido, and phosphoryl groups. Each of these transformations deserves a separate lecture. In what follows, I will present several examples describing some of these CH functionalizations. Here, I want to briefly describe the range of reagents suitable for a given CH transformation. This should give you an idea of the amount of work that has been done in CH activation within the last few years. Here, the scope of reagents suitable for CH arylation is presented. The most popular reagents are aryl halides. Additionally, CH arylation can be accomplished by using derivatives of phenol, iodonium salts, aryl organometallics such as boronic acids and organosilicon reagents, as well as derivatives of carboxylic acid and sulfonic acid, among others. Now, let's consider the range of coupling partners suitable for CH alkylation. In this case, the most frequently used reagents are olefins and alkyl halides. Additionally, you often come across examples of CH alkylation based on the application of derivatives of alcohols, sulfonic acid, and sulfoxides, carboxylic acids, organometallic reagents, ammonium salts, unfunctionalized activated systems like CH acids, and carbene precursors, among others. The mechanisms of CH alkylation can be quite diverse, predominantly depending on the coupling partner used. The most frequently used reagents for trifluoromethylation include the Rupert-Prakash reagent, as well as the reagents developed by Tanyi and Omamoto. For CH carboxylation, one can apply radical initiators like azo-bisobutyronitrile, keto acids, derivatives of formic acid, isocyanates, nitromethane, and carbon monoxide, as well as CO2. The final transformation I want to present here is CH amination, which can be achieved by the application of amides, amines, and anilines, as well as derivatives of hydroxylamine and azides, among others. Once again, the mechanism of CH amination mainly depends on the reagent used. To sum it up, this lecture covered the main factors controlling the reactivity and selectivity in CH activations. You witnessed that the most prominent approach used to control selectivity in CH transformations is based on the use of directing groups. You were introduced to the main types of CH activations and common reagents used for selected CH transformations. The next lecture will cover the most important mechanisms of CH bond cleavage enabled by transition metals. Thank you for your attention. Hello everyone, and welcome back to the series of lectures on CH activation. In the previous learning materials, we covered the main definitions of CH activation and discussed the factors controlling the reactivity of CH bonds and the selectivity of CH transformations. In this lecture, I will summarize the main mechanisms of CH bond cleavage enabled by transition metals. Most transition metals are capable of activating and cleaving CH bonds through one of the mechanisms I am going to describe. Here, I will show you only the stage of CH bond cleavage. Later, complete mechanisms on representative examples will be discussed so you can see the full catalytic cycles. The following three mechanisms are typical for the activation of CH bonds in all three hybridization states of carbon. The first mechanism is based on the oxidative addition of the metal to the CH bond. This type of CH activation is common for late transition metals in their low oxidation state. The second mechanism of CH activation is based on sigma bond metathesis, common for early transition metals. The next mechanism shares some similarities with enzymatic CH activations occurring in nature and is based on photoredox catalysis. In this case, the catalyst being activated by light abstracts electrons from the substrate or donates electrons to the substrate, generating radicals, cations, or other reactive intermediates that further undergo coupling reactions. The main catalysts in this case are based on iridium and ruthenium. Moreover, transition metals are known to greatly facilitate the selective CH insertions of carbons and nitrines. This chemistry works well with late transition metals, including iron, rhodium, and ruthenium. The following two mechanisms are typical for the activation of sp2 hybridized CH bonds. For instance, CH activation can occur via Heck-type insertion followed by a beta hydride elimination. This mechanism is typical for rhodium, palladium, and copper. The final mechanism of CH activation shares some similarities with electrophilic aromatic substitution and is known by the name concerted metalation-deprotonation. It can also operate for some sp3 hybridized CH bonds. This mechanism is typical for late transition metals in their high oxidation states, and it works well for electron-rich aromatic systems. Now, let's delve into specific examples, starting with CH activation through the oxidative addition of the metal to the CH bond. This mechanism is typical for late transition metals in their low oxidation states. For instance, if you encounter a CH transformation catalyzed by iridium-1 or rhodium-1 complexes, it's likely that the reaction proceeds via the oxidative addition of the catalyst to the CH bond, generating iridium-3 or rhodium-3 intermediates. These intermediates, through subsequent elementary reactions, will lead to the formation of the product resulting from CH activation. As an example, let's consider the iridium-catalyzed CH alkylation of urea derivatives. In this reaction, the amide acts as a directing group, guiding iridium-1 to the nearest CH bond. The oxidative addition of iridium-1 to the CH bond generates an iridium-3 cyclometylated intermediate, which undergoes a syn insertion into the olefin, generating this intermediate. The final stage of the process is reductive elimination, which, upon hydrolysis, produces the product and regenerates the active catalyst, iridium-1. The next example is the rhodium-catalyzed silylation of aromatic compounds, published in 2008. The mechanism is quite similar to the previous one. A ligand substitution reaction occurs at rhodium, accompanied by the cleavage of the silicon-silicon bond. The formed rhodium-1 intermediate, after coordination to the directing group, undergoes oxidative addition to the CH bond, generating this rhodium-3 intermediate. The final stage of the catalytic cycle is reductive elimination, producing the product and regenerating the active catalyst, rhodium-1. The next mechanism is CH activation via sigma bond metathesis. Whenever you encounter a CH transformation catalyzed by early transition metals, you should think about sigma bond metathesis. As an example, I want to show you the yttrium-catalyzed alkylation of aniline derivatives, published in 2016. Before we delve into the mechanism, I want to offer a word of caution. This will perhaps be the most challenging part of today's lecture. Here we go. In the first step of the process, the trityl carbocation displaces one of the sigma-bonded ligands of yttrium, generating the active catalyst. This active catalyst initially coordinates to the nitrogen of the substrate, followed by CH bond cleavage via sigma bond metathesis. Subsequently, an olefin coordinates to the generated complex, initiating a hec-type insertion through a process quite similar to sigma bond metathesis. Next, the generated intermediate undergoes ligand substitution with another molecule of aniline, resulting in this intermediate. The final stage of the process involves the CH bond cleavage of the newly coordinated substrate via another sigma bond metathesis, leading to the formation of the product and the active catalyst, now possessing another substrate. The following mechanism is CH activation via photoredox catalysis. These processes are mostly radical, so whenever you encounter iridium bipyridine or ruthenium bipyridine complexes, you should think about photoredox catalysis. Let's consider the first example, the ruthenium and cobalt co-catalyzed intramolecular thiolation of arones published in 2015. The initial step of the process is the deprotonation of the thioamide, followed by a single electron transfer from the substrate to the photoactivated ruthenium catalyst, generating the following radical. The sulfur-centered radical attacks the aromatic ring, producing a more stable radical, which undergoes a one-electron oxidation by the cobalt catalyst, forming a cationic intermediate. The final stage of the process is the elimination of a proton, producing the benzothiazole. The eliminated proton oxidizes the reduced cobalt-1 to the active cobalt-3, generating hydrogen gas. Overall, we have 3 single electron transfer processes and 2 interconnected catalytic cycles. The next example is an iridium-catalyzed intramolecular amination of the benzylic CH bond with N-halogenated tosylates, published in 2015. In this case, the photoactivated iridium-3 catalyst donates an electron to the substrate, generating this N-centered radical. The radical abstracts a hydrogen atom from the benzylic position, creating a more stable benzylic carbon-centered radical. In the next stage of the process, the formed radical undergoes a one-electron oxidation by an iridium-4 intermediate, regenerating the active photocatalyst and producing a benzylic carbocation. This carbocation undergoes intramolecular coupling with the amide, forming the product and releasing a proton. In this example, the activated photocatalyst donates an electron to the substrate, while in the previous example, the activated photocatalyst took an electron from the substrate to initiate the reaction. Both processes are possible, and the outcome depends on the substrate and reaction conditions. CH transformations occurring in nature are mostly radical processes and share some similarities with CH activations by photoredox catalysis. Notably, in nature, CH activations are catalyzed by metalloenzymes, particularly by cytochromes located in our livers. For instance, one can observe the couplings of phenols, anilines, and their derivatives catalyzed by cytochromes. Initially, the enzyme abstracts an electron and a proton from the substrate, which can then undergo a number of selective radical couplings, forming carbon-carbon or carbon-heteroatom bonds. The selectivity of these processes is determined by the enzyme. In contrast to photoredox catalysis, enzymes typically do not require a source of light for these transformations. Now, let's consider the CH insertion of carbons and nitrines. Whenever you encounter azides or diazo compounds combined with late transition metals, you should think about the CH insertion of carbons and nitrines. The first example is an iron-catalyzed intramolecular CH amination of arones by corresponding azides, published in 2016. The reaction was conducted under microwave irradiation, typical for diazidization reactions. In the first stage of the process, the substrate loses nitrogen and forms an iron-nitrene complex. It is proposed that the formed complex undergoes several electron shifts, as shown here, forming the carbazole and the active form of the catalyst. The next example is an iron-catalyzed intramolecular allylic alkylation with diazo compounds. Initially, the substrate loses nitrogen, accompanied by the formation of the corresponding iron-carbene complex. In contrast to the previous example, in this case, electron shifts produce intermediate radicals that eventually undergo intramolecular radical coupling, yielding the product and regenerating the active catalyst. CH activation via Heck-type insertion is less studied and is debatable. However, whenever you encounter a late-transition metal-catalyzed CH activation of a 5-membered heterocycle with low resonance energy, such as furans, you should consider the possibility of this mechanism. This mechanism was proposed for the palladium-catalyzed CH arylation of furans possessing an electron-withdrawing group. According to the proposed mechanism, the reaction starts with the oxidative addition of palladium-0 to the aryl halide, generating the corresponding palladium-2 complex. Further, this complex undergoes a Heck-type insertion into furan, followed by beta-hydride elimination to generate the product and a palladium-2 hydride intermediate. The active catalyst is regenerated by the reductive elimination of hydrobromic acid, which is trapped by the base. Now let's consider the last mechanism, CH activation via concerted metalation-deprotonation. This mechanism is typical for late transition metals in their high oxidation states. Therefore, whenever you encounter ruthenium-2, rhodium-3, iridium-3, or palladium-2 complexes combined with bases like acetate or carbonate, you should think about this mechanism. The first example is the iridium-catalyzed CH amination of arones published in 2015. Before I show you the mechanism, pay attention to the reagents used by the authors. They employed iridium-3 as a catalyst, a silver salt, and copper pivolate. The silver salt serves multiple roles in this process. Firstly, it removes chlorides from iridium, forming the active catalyst, and it can also act as an oxidant. The active form of the catalyst coordinates to the directing group and undergoes a concerted metalation-deprotonation sequence, forming the cyclometylated intermediate shown here. The formed intermediate undergoes a ligand substitution involving the amine, followed by the double oxidation of the system by silver, generating a nitran complex of iridium-5, as shown here. This is followed by reductive elimination and protonolysis, leading to the product and the regeneration of the active catalyst. The final example for today is the ruthenium-catalyzed CH olefination of arones, published in 2012. In this case, as well, the initial step of the process involves silver-mediated formation of the active form of the catalyst through the substitution of chlorides by acetates. The active form of ruthenium-2 first coordinates to the substrate, followed by a concerted metalation-deprotonation sequence forming this cyclometylated intermediate. The next step of the process includes a Heck-type insertion, followed by beta-hydride elimination, generating the product. The active catalyst is reproduced through a sequence of reductive elimination followed by the oxidative regeneration of the ruthenium-2 catalyst, enabled by copper-2 acetate. To sum it up, in this lecture, we have learned the main mechanisms of CH bond cleavage initiated by transition metals. Accordingly, CH activation can occur via oxidative addition to the metal, sigma bond metathesis, photoredox catalysis, Heck-type additions, and a concerted metalation-deprotonation sequence. In the next lecture, we will concentrate on the modern developments in CH activation. Thank you for your attention. Greetings to all and welcome back to the series of lectures on CH activation. So far, we have examined the main pathways of transition metal-initiated CH bond cleavages. We observed that maintaining the selectivity of CH transformations is crucial, requiring directing groups capable of coordinating to the catalyst and guiding it to the nearest CH bond. The present lecture will cover selected applications of modern directing groups in regioselective CH activations. Here, once more, one can observe most of the directing groups developed during the last 2 decades. A common feature for most of them is that they are connected to the main molecule via a carbon-carbon bond. As you know from the general organic chemistry course, carbon-carbon bonds are not easily accessible for chemical transformations, meaning that the removal or further functionalization of these directing groups is almost impossible. The inertness of these directing groups may become a serious issue during multi-step processes where all the functional groups need to be removable or modifiable. This drawback has motivated many scientists to work on the development of novel directing groups that can be easily introduced to the molecule undergoing CH transformation and subsequently removed or modified if necessary. As a result, a number of removable or modifiable directing groups were introduced. The most important examples for aromatic systems are presented here and described in the review articles below. As you can see, most of the removable or modifiable directing groups are based on pyridine connected to the main molecule by a carbon heteroatom bond. Other interesting examples include silanols, protected boronic acids, and nitro compounds. The only removable directing group based on a carbon-carbon bond is the carboxyl group. However, this strategy has limited scope because decarboxylation requires harsh conditions. For obvious reasons, there is not a single removable or modifiable directing group suitable for CH activation of unfunctionalized aliphatic compounds. However, for functionalized aliphatic compounds, such as aliphatic amines or alcohols, there are some removable directing groups that are typically attached to the functional group within the molecule. Now, let's explore a few examples in more detail. Let's consider the pyridine directing group attached to the main molecule via a carbon-silicon bond, developed by the group of Gevorgian from the University of Texas at Dallas. In one of their initial reports, they described a palladium-catalyzed CH halogenation of aromatic compounds directed by the removable pyridyl group shown here. As one can see, the substrate scope is quite broad, allowing for the presence of various reactive functional groups such as halogens and esters. In most cases, the yields of the reaction were quite high. They could demonstrate that afterward, the directing group can be easily removed or transferred into other useful functional groups, such as halide, ester of boronic acid, and hydroxyl group. In the following reports, they described the introduction of the directing group into the molecules undergoing CH activation. However, it was found that this task is not easy and necessitates the use of expensive reagents. To establish proper conditions, more than 40 experiments were conducted. Another limitation arises from the fact that the removable directing group is not stable in the presence of bases, rendering it unsuitable for CH functionalizations requiring the use of fluorides and other strong bases. The nitro group is another highly promising directing group. Its advantage over others is attributed to the fact that it can be converted into essentially anything. The main disadvantage is that the nitro group, being a strong electron withdrawing group, makes the systems to which it is bound less reactive. As an example, let me share with you the work performed by the group of Langer at the University of Rostock, Germany. They have developed a palladium-catalyzed methodology suitable for the selective CH arylation of several heterocyclic systems. These conditions were quite successful for imidazoles, pyrazoles, and purine-like compounds. For 2,5-unsubstituted imidazole, it was found that the reaction proceeds regio-selectively towards arylation at the 5th position when using 1.1 equivalents of aryl halide. In this case, position 2 can be arylated by the addition of another aryl halide. When the arylating reagent is used in excess, the main product of the reaction is a diarylated imidazole. This is another example where the directing effect is more dominant than the inherent reactivity of the system. In the case of pyrazoles, further optimization showed that position 3 can be arylated in the presence of an excess of copper iodide. Based on this finding, it was possible to prepare 3,5-diarylated pyrazoles, each possessing 2 different aryl groups. The potential of the nitro group as a useful directing group was demonstrated through several model transformations. For instance, the reduction of the nitro group under different conditions led to the formation of anilines, dimethylated anilines, and derivatives of phenanthridine. Additionally, the nitro group was transformed into a bromide, enabling the introduction of aryl, alkenyl, and alkenyl groups using Suzuki, Sonogashira, and Heck cross-coupling reactions, respectively. The next example is the CH acetoxylation of aliphatic alcohols developed by the group of Dong from the University of Texas. They applied derivatives of hydroxylamine as a removable directing group for the functionalization of aliphatic systems. With the directing group presented here, they have examined several oxidative CH transformations enabled by palladium catalysts. For CH-acetoxylation, the best catalyst was found to be palladium acetate combined with stoichiometric quantities of a high-pervalent iodine reagent, phenyliodine diacetate, which acts as a source of acetate and an oxidizing agent. As one can see, the reaction operates on both acyclic and cyclic alcohol derivatives. Furthermore, they have demonstrated that the directing group can be selectively removed under two different conditions, including basic hydrolysis and zinc-mediated reduction. Under these conditions, the newly introduced functional group remains intact. In this case, the introduction of the directing group was easier and took two steps. First, they substituted the hydroxyl group of the alcohol with N-hydroxyphthalimide, followed by deprotection of the amino group and the formation of a Schiff base with an aldehyde. To sum it up, in this lecture, we examined the main removable directing groups used in selective CH transformations. We explored the principles underlying the development of removable and modifiable directing groups and specifically focused on CH transformations guided by the pyridine directing group attached to the main molecule via a carbon-silicon bond, nitro group-directed CH arylations, and hydroxylamine-based directing groups used in aliphatic systems. In the following lecture, we will delve into two additional families of directing groups, demonstrating added value. Thank you for your attention. Greetings to all, and welcome back to the module on CH activation. In the previous lectures, we learned about traditional directing groups that determine the selectivity of CH transformations. We also examined removable and modifiable directing groups, which open new avenues for sophisticated organic synthesis based on CH activations. In this lecture, you will learn about other important families of directing groups, offering new perspectives for atom economy and synthesis. A promising direction in CH functionalization is based on the use of so-called oxidizing directing groups. Many CH transformations, in addition to the catalyst, require stoichiometric quantities of an oxidant. The most effective oxidants for CH activation have proven to be salts of silver 1 and copper 2. However, these salts are quite toxic and expensive. Therefore, finding less toxic and inexpensive oxidants is an ongoing task. An interesting solution to this issue was recently developed and is based on the application of directing groups possessing functionality that can act as an oxidant for the catalyst. The main representatives of oxidizing directing groups are presented here, with most of them based on derivatives of hydroxylamine where the nitrogen-oxygen bond is responsible for the oxidation of the catalyst during the catalytic cycle. Additionally, it has been recently discovered that N-oxides and derivatives of hydrazine may also act as an oxidizing directing group. So far, all the known CH transformations enabled by oxidizing directing groups have been based on aromatic systems. Unfortunately, I was not able to find any oxidizing directing group suitable for the oxidative CH transformation of aliphatic compounds. Hopefully, one of you will develop one in the future. Here is an example of a CH functionalization enabled by an oxidizing directing group. The group of you from Sichuan University developed a rhodium-catalyzed, external oxidant-free, CH-olefination of aniline derivatives, as presented here. They used aniline N-oxides as the oxidizing directing group. The substrate scope involved various aniline derivatives and different Michael acceptors. Rhodium-3 is involved, so the CH activation occurs via a concerted metalation-deprotonation sequence, as shown here. The reaction starts with the activation of the rhodium complex through ligand substitution reactions. This is followed by the coordination of the substrate and CH activation via a concerted metalation-deprotonation sequence. Next, we have olefin insertion, followed by beta hydride elimination, leading to the formation of this rhodium-3 intermediate. In the last steps, there is a reductive elimination of pyvalic acid, resulting in a rhodium-1 intermediate. The rhodium-1 intermediate undergoes oxidative addition to the N-oxide, followed by protonolysis and ligand substitution, regenerating the active rhodium-3 catalyst. This process is accompanied by the release of the orthoolefinated aniline. The directing effect of N-oxides was demonstrated by isolating the cyclometylated intermediate presented here, which, in the presence of acrylate, leads to the formation of olefinated aniline in a 42% yield. The preparation of starting N-oxides is quite simple and can be achieved by oxidizing aniline derivatives with metachloropyroxybenzoic acid. Here is another extension of the directing group strategy. A modern variation of removable directing groups is known as transient directing groups. This strategy is based on reversible reactions. For instance, if your substrate contains a functional group that may not serve as an effective directing group but can be reversibly transformed into other functional groups, you can apply this strategy using a directing group that can be attached and detached to your functional group during the reaction. Let me provide some examples to make everything clear. For instance, aldehydes are not good directing groups for late transition metals. However, in the presence of catalytic amounts of primary amines, they can be reversibly transformed into corresponding Schiff bases, which serve as far better directing groups. After the CH transformation, the Schiff base can be hydrolyzed back to the corresponding aldehyde, allowing the amine to be used in catalytic amounts. Based on this strategy, recent developments include CH arylation, halogenation, hydroxylation, amination, and borylation reactions. Applying the same concept, it is possible to selectively functionalize phenols using transient directing groups based on phosphonite. In this case, a reversible transesterification at phosphorus generates phosphonites derived from the initial phenol, with phosphorus serving as a directing group for the catalyst. In situ formation of Schiff bases was also applied for CH transformations of aliphatic carbonyl compounds. This approach can be employed for both aliphatic aldehydes and ketones. A similar strategy can be applied to CH transformations of aliphatic amines. However, in this case, one needs to use a directing group possessing an aldehyde functionality. Let's go through two examples in more detail. The group led by you from the Scripps Research Institute was among the first to develop this chemistry. In their recently published work, they identified 3 different transient directing groups for metal-catalyzed CH halogenation, arylation, and amination reactions. All were based on in situ Schiff base formation between the starting aldehyde material and transient directing groups, which included various anilines and amino acids. A portion of the substrate scope is presented here. As one can observe, the developed conditions tolerate numerous reactive functional groups, and the yields are above average. The developed approach was so successful that it could be extended to the late-stage CH functionalization of an analog of the commercial drug Celecoxib. Celecoxib is a nonsteroidal anti-inflammatory drug and is one of the top-selling drugs in the world. The group led by you was among the first to extend this strategy to aliphatic systems. For aliphatic primary amines, they identified a suitable transient directing group based on aldehydes, enabling the palladium-catalyzed CH arylation described here. The optimal reaction conditions are presented here. This CH arylation worked with palladium-based catalysts combined with silver salts used in stoichiometric quantities. They screened several transient directing groups, among which the underlying pyridine derivative showed the best results. Furthermore, they applied the developed strategy for the direct CH arylation of various aliphatic amines. The scope of the reaction includes both cyclic and acyclic amines. It should be noted that, after the CH arylation step, they protected the amino group to facilitate the separation process. To sum it up, we have seen that directing groups can play a dual role in CH transformations. It is possible to include additional functionalities in the directing group that can act as an oxidant for the catalyst, thus eliminating the need to use an external oxidant based on salts of precious metals. The directing group does not have to be permanently bound to the substrate being functionalized. Transient directing groups can enter the substrate and, after selective functionalization, leave the product. This strategy is based on reversible reactions, meaning that transient directing groups can also be used in catalytic quantities. Now, you are familiar with the main directions in regioselective CH transformations enabled by directing groups. The directing groups discussed so far guide the catalyst to the ortho-CH bonds, which are normally the nearest CH bonds to the group. In the coming lecture, I will describe strategies for the regioselective functionalization of more remote CH bonds. Your attention and participation are greatly appreciated. Hello everyone, and welcome back to the series of lectures on CH activation. In our previous session, we delved into the factors influencing selectivity in CH transformations. We examined the main pathways of CH bond cleavage enabled by transition metals, and I introduced the concept of directing group-assisted CH activation. So far, I have described only direct CH transformations of CH bonds located ortho to the directing group. But what about meta and para positions? With modern developments in directing group-assisted CH activation, it is now possible to selectively functionalize even remote CH bonds. For instance, there are 4 strategies available for meta-selective CH transformation. The first one is based on the application of directing groups connected to the substrate through a special template. This template is designed so that the directing group appears in close proximity to the meta-CH bond, directing the catalyst to that position. The second approach operates only on substrates possessing a hydrogen bond acceptor. In this case, the catalyst is used in combination with a specialized ligand, which, along with coordination to the catalyst, can act as a hydrogen bond donor, as described here. Overall, this rather complex system positions the catalyst near the meta-CH bond that is being activated. This strategy has some similarities with the application of transient directing groups. The following strategy is based on the Catalani reaction, which you may recall from the lectures on cross-couplings. The key point of the Catalani reaction is that the addition of norbornene to aromatic systems is reversible. If a typical directing group is present in the molecule, the first step of the process involves directing group-assisted orthoalkylation with norbornene. Instead of beta hydride elimination, the formed intermediate undergoes another CH activation sequence, followed by the elimination of norbornene. The described sequence leads to the formation of a meta-substituted product. The final approach is based on the application of ruthenium paraselective complexes. In some cases, cyclometallation products of ruthenium are quite stable and can have an activating effect on the substrate. In the product of cyclometallation, the CH bonds of the substrate indicated in red are sterically hindered due to the directing group and the ligands on ruthenium. Therefore, the second molecule of the catalyst can only functionalize the meta-CH bond indicated in blue. Except meta-functionalization, the strategy based on the use of specialized templates and directing groups was recently extended to para-CH functionalization of aromatic systems. Now, let's briefly go through some specific examples. The template strategy for meta-CH activation was developed by the group of you at the Scripps Research Institute. Their initial paper was published in 2012. They have developed two directing groups, both suitable for palladium-catalyzed meta-CH olefination. A short optimization was required for this directing group, eventually indicating that the best meta-selectivity can be achieved when R1 and R2 are isobutyl and tert-butyl groups, respectively. The substrate scope is presented here. Following their report, it should be mentioned that the reaction works well for a wide range of substrates, producing corresponding meta-olefination products in good yields. They successfully applied their strategy for the late-stage CH functionalization of the commercial drug baclofen, although in this case, they obtained a 1-to-1 mixture of mono and disubstituted products. The approach based on the hydrogen bonding of specialized ligands and the substrate was developed in the group of Kanai at the University of Tokyo. They conducted studies on iridium-catalyzed CH borylation on amides and related hydrogen bond acceptors. To enhance the selectivity of the reaction toward the meta position, they screened a number of ligands as described here. The table presents not only the yield of the product, but also the ratio of meta and para-substituted products. The best meta-selectivity was observed when using the ligand with R equal to a cyclohexyl group. The overall yield of the product was further increased by replacing the solvent hexane with para-xylene. In here, one can observe the scope of the reaction. Their strategy proved successful not only for substituted benzenes but also for heteroarenes. Hydrogen bond acceptors such as amides, esters, and phosphonates were applied. The role of hydrogen bonding in the selectivity of the reaction was also examined. Any manipulations involving the positioning of the urea subunit significantly decreased the selectivity. Likewise, the replacement of hydrogen atoms with alkyl groups in the urea subunit also led to a decrease in selectivity. The approach based on the application of norbornene was primarily studied in the group of you. In their recently published work, they examined palladium-catalyzed meta-CH amination using derivatives of hydroxylamine. It is worth mentioning that, instead of norbornene, they used a derivative of norbornene indicated in red. The researchers found that the reaction proceeds well only in the presence of pyridine-based ligands. Among others, the underlying ligand showed the best efficiency. The exact function of the ligand is not clear, and overall, compared to traditional cross-couplings, the role of ligands in CH activations is not well understood. After optimizing the reaction conditions, they studied the scope and limitations of the process. In general, the reaction proceeds well for a wide range of substituted arones, producing corresponding amination products with good yields and selectivity. In the same paper, they also described meta-CH alkylation of arones using a similar strategy. For this new transformation, they changed the pyridine-based ligand and applied alkenyl bromides as coupling partners. For meta-CH activation enabled by cyclomethylation, let me share the work conducted by the group of Ackermann from the University of Göttingen. In their 2017 publication, they explored ruthenium-catalyzed difluoromethylation of various arants. The study revealed that difluoromethylation can be achieved using a variety of directing groups. The most promising results were observed with pyridines, pyrimidines, indazole, and pyrazoles. Interestingly, applying the same strategy made it possible to introduce monofluoroalkyl groups. Furthermore, they successfully extended their strategy to purine derivatives. Difluoromethylation proved effective for purines with a protected sugar. This concludes the strategies for meta-CH functionalization. Now, let's explore an example of selective para-CH transformation. The strategy based on specialized templates and directing groups was extended to para-CH functionalization in the group of MITI from the Indian Institute of Technology. They investigated the palladium-catalyzed CH olefination of derivatives of phenol, as described here. Initially, they screened several templates, including control experiments without directing groups. It was found that unprotected phenols are not reactive, while protected phenols can be olefinated, though with poor selectivity. They observed good para-selectivity using the specialized template with a cyano group, which acts as a directing group for the catalyst. On this slide, one can observe the scope of the reaction. The brackets present the ratio of products with para-selectivity over others. The reaction performs well with a variety of substituted arans and Michael acceptors. They demonstrated that the template with the directing group can be removed through acid-catalyzed hydrolysis and later reused for another substrate, as described here. So far, I have shown you only examples in aromatic systems, as the functionalization of remote CH bonds in aliphatic systems is far less studied. In this context, the work by the group of Sanford from the University of Michigan is unique and highly promising. They successfully developed proper conditions and directing groups for the palladium-catalyzed CH arylation of aliphatic CH bonds located at gamma or other remote positions. Another noteworthy finding was that, for some cases, the functionalization of remote positions was only possible in unstable conformations of cyclic systems, such as the boat conformation of piperidine presented here. The reaction conditions were optimized for this bicyclic amine, and part of the optimization table is presented here. The best directing group turned out to be the amide possessing a perfluorinated aniline. To minimize the formation of intramolecular amination byproducts, the silver salts were replaced by cesium pivalate, as silver, among other roles, can act as an oxidant, promoting intramolecular amination. Following the optimization, they screened the scope of aryl iodides. The yields were moderate, but the regioselectivity and chemoselectivity of the reaction were exceptional. Additionally, they explored the scope of cyclic amines, which was quite impressive. Although the yields of the products were not very high, and in some cases, they observed double arylation. Hopefully, in the near future, we will see some extensions to this chemistry. To sum it up, in this lecture, you have been introduced to the main concepts applied for the selective CH functionalization of remote positions. For aromatic systems, it is possible to design specialized templates for directing groups and ligands, guiding the catalyst to the meta position. Alternatively, meta-selective CH transformations are achievable via the modified Catalani reaction or through cyclometylated intermediates blocking the ortho positions. The template strategy for remote CH functionalization can be extended to para positions, and CH activation at remote CH bonds of aliphatic systems is also achievable. These were the main modern directions in CH activation. I encourage you to proceed to the concluding lecture of the module, where I will describe selected applications of CH functionalizations. Thank you for your attention. Greetings to all and a warm welcome to the concluding part of the module on CH activation. In this course, you learned the basic concepts about CH activation. We systematically covered the main mechanisms of the CH bond cleavage initiated by metals, the selectivity determining factors in CH transformations, and some modern directions in the field of CH activation. This lecture is devoted to the description of selected applications of modern developments in CH functionalization. Traditional approaches to conjugated oligomers and polymers are based on cross-coupling reactions. The first option involves the coupling of arans possessing two organometallic functionalities with dihalogenated arans. The second option is based on the self-coupling of arans possessing both organometallic and halide functionalities. Conjugated oligomers and polymers prepared by these methodologies can be applied as organic semiconductors, fluorescent probes, etc. Selected examples can be seen here. Similar oligomers and polymers can be prepared using CH activation of aromatic systems. The replacement of traditional cross-couplings by modern direct CH arylations can revolutionize this field of research, as CH activations demonstrate high atom economy and sustainability. The research on thiophene conducted by the group of Doucet from the University of Rennes has significantly influenced modern developments in this field. The Doucet group has published over 150 papers describing highly efficient palladium-catalyzed CH arylations involving thiophenes, perhaps the most extensively studied systems among arants. Consequently, oligomers and polymers demonstrating promising properties are currently prepared by palladium-catalyzed CH arylation of thiophene derivatives, as described in this general scheme. The list of the most frequently used thiophene derivatives is shown in red, while the most important aryl halides are indicated in blue. Modern developments in CH activation have found applications in the total synthesis of natural products and other complex systems. In here, you can see Dragmacidin D, a natural product isolated from sponges. The group led by Atami from Nagoya University suggested and successfully performed the total synthesis of this natural product, mainly relying on direct CH transformations. Specifically, they utilized multiple CH arylations, as will be described in what follows. They began with the palladium-catalyzed CH arylation of the silyl-protected thiophene, using an iodinated indole derivative. In the next stage, they performed the reductive desulfurization of the newly introduced thiophene, followed by the replacement of protecting groups at nitrogen and oxygen with a methoxymethyl protecting group, abbreviated as MOM. This step was succeeded by a palladium-catalyzed oxidative arylation at the third position of the indole with the N-oxide of pyrazine. Subsequently, an acid and hydride-mediated intramolecular migration of the oxygen atom from the N-oxide to the second position of the pyrazine ring was carried out. This was followed by an acid-catalyzed electrophilic substitution at the indole ring of 6-bromoindole. At this stage, Friedel-Crafts chemistry was involved, distinct from CH activation. During this process, methoxymethyl protecting groups were removed as they are labeled under acidic conditions. In the final stage of the synthesis, they halogenated the alpha position of the carbonyl subunit, followed by cyclocondensation with guanidine to afford the imidazole ring. Overall, the synthesis included 2 CH arylations and a Friedel-Crafts arylation. Now, let me describe 2 examples of the synthesis of commercial pharmaceuticals. The production of the anti-inflammatory drug Diclofenac can involve a CH activation step. In 2010, the group led by you developed a palladium-catalyzed approach for carboxyl-directed CH iodination of arants. Their methodology was quite successful for a range of substituted arants, as presented here. The reaction worked well even for electron-deficient substrates, which are normally inactive for electrophilic aromatic substitutions. As a potential application of this reaction, they suggested and successfully performed the synthesis of diclofenac. They prepared the iodinated phenylacetic acid using palladium-catalyzed CH iodination, followed by copper-mediated Ullmann amination to yield diclofenac in 61% yield. In another paper, scientists from Pfizer developed a novel approach to celecoxib involving a CH arylation step. Initially, they prepared the sulfonamide, which was subsequently coupled with a trifluoromethylated pyrazole via copper-catalyzed Ullmann amination. The resulting pyrazole derivative was selectively arylated at position 5 using palladium acetate combined with Beller's ligand. The subsequent deprotection of the sulfonamide gave celecoxib in a 69% yield. One of the key approaches in modern drug discovery involves the late-stage functionalization of potential drug candidates or commercial drugs. This method allows for the rapid preparation of libraries of biologically active substances for biologists. The modern developments in CH activation can greatly facilitate drug discovery through late-stage CH functionalization, as demonstrated in previous lectures. Here is another interesting example of late-stage CH functionalization, elaborated by the group of Baron in collaboration with scientists from Leo Pharma. The focus of their work was on analogs of the antibacterial natural product Hongoquercin A. They prepared 2 analogs with directing groups such as perfluorinated amide or carboxyl group. Utilizing directing group-assisted CH functionalization, they successfully introduced a variety of functional groups into these molecules. This included CH aminations, arylations, amidations, olefinations, hydroxylations, and alkylations. Further biological examinations revealed that the prepared analogs of Hongoquercin A demonstrated enhanced antibacterial activity. To sum it up, modern developments in CH functionalization allow for the effective synthesis of materials, natural products, pharmaceuticals, and biologically active ingredients. Further advancements in the field may eventually replace traditional cross-coupling approaches, which rely on pre-functionalized starting materials, with direct CH transformations. In conclusion, I want to highlight the scientists who have made a significant impact on the development of CH activation. All the academics described here have well-established websites detailing their research and publications. If you wish to delve deeper into a specific CH transformation, I encourage you to explore the works of the researchers mentioned below. The actual boom we have witnessed in this field was driven by the development of pyridine-based directing groups in the Sanford group. The group led by U has also contributed significantly by developing many other efficient directing groups and transformations. The research conducted by Sanford and U was primarily focused on aromatic systems. Key advancements in directing group-assisted CH transformations of aliphatic compounds were made in the groups of Dogulus and Chatoni. Here are some other scientists who have made a significant impact on the development of selected aspects of CH activation. For instance, if you are interested in CH arylation, I would suggest considering the works of Fongnil. If hydroarylation via CH activation catches your interest, you should explore the research from the groups of Bergman and Ellman. For those intrigued by photoredox catalysis, the works from Macmillan's group are worth exploring. If the application of first-row transition metals in CH activation is your focus, Ackermann's group has valuable contributions. CH insertion of carbons was predominantly studied by the Davis group, while for the insertion of nitrines, you should check the works from Dubois group. For CH metallation, refer to the works from Miura and Hartwig. Hartwig, among others, is renowned for systematic studies on the mechanisms of selected CH transformations. Oxidative and radical CH transformations were primarily studied in Lay's group. If you are interested in the total synthesis and applications of CH activation, you should explore the works from the groups of Barron and Atami. Finally, for those interested in understanding exact mechanisms and theoretical studies on CH activations, checking the works from the groups of Schoenbeck, Gorelsky, and Musaev is recommended. Most of these scientists used to be part of a scientific community known as the Center for Selective CH Functionalization, led by Hugh Davies. They have an official website and a YouTube channel where you can find numerous videos covering modern trends in the field. While I believe the Center for Selective CH Functionalization is no longer active, the valuable material and wonderful lectures produced in the center are still available. I appreciate your time and thoughtful consideration. Best wishes for your midterm evaluations and continued success throughout the rest of the course.